Okay, now we go to business side. So Blueforce, they have started to do business out from quantum technology, and David Gunnarsson is here to tell cryogenics role in quantum technology.
Okay.
You're welcome.
Thank you, Jussi. So let's see. So, as Jussi said, my name is David Gunnarsson. So I work at Blueforce, and I'm here today to talk a little bit about cryogenics role in quantum computing. And in Mikko's talk, there was actually no talk about cryogenics, which actually is a good thing for me. So that was actually good, because it means that it's something that is not a problem. I think the problem lies elsewhere at the moment.
Yes, you are so good.
Yes. Thank you. So my background is actually, this is quite familiar place to me. I've been working here both in Aalto and VTT, so it's nice to be back. There's a lot of familiar faces here. But today I will talk a little bit more about Blueforce perspective on quantum technology from the role of cryogenics and what we see the future will be in at least the nearest future for us as a business. So to start, I will give a little bit background to the company, because I want to describe how because cryogenics, especially the cryogenic that Blueforce are doing, is a very scientific field. So it's not natural that this grows as a business as it has done. So to give the background how the company has sort of been founded and how it has grown the last 11 years is quite a very interesting story. So it was founded here in Otaniemi by Rob Blaugvers and Peter Vosenman. So they worked on a new type of dilution refrigerator, which is sort of the core business of Blueforce. The prototype is still running here in the low temperature lab, and the company started in Otaniemi a few years, and then when it grew bigger, it moved to Helsinki, to Pitkäjänmäki, and that's where we have our headquarters and our factory at the moment. Today we are 150 employees, or close to 150. We have some positions to fill, and we are actually 15 nationalities working in the company, so which we are very proud of. So that tells you that the expertise needs to come from everywhere in this field also. And if you look at our business success, we have more than 400 systems delivered in the world. And if you're not familiar to this system, that maybe don't tell so much, but if one look at the company in real numbers instead, one can see how the growth has been from the start 11 years ago until now. So last year we already had a revenue close to 50 million euros, and we already have a projected revenue for next year that is 60 million euros. So you can actually do business and earn money on quite complicated systems. And of course, what has sort of triggered this growth is of course why we are here today. So it's quantum technology, specifically quantum computing. That is the thing that have driven our business, the research in that field has. And I think the big point was around this point. That's when it started to become more and more interesting for also commercial R&D in this field. So if one take a step back and look what was changed 11 years ago, because of course when Blueforce was founded, they did something new with cryogenics. Because cryogenics used to look like this, or it actually still looks like this, maybe in some places, but but it was very inaccessible. You needed an infrastructure to have cryogenic liquids, and the systems you had, they needed a quite high threshold of use of the user. You needed to actually be trained quite a long time to operate them safely. You needed to maintain them a lot. You actually had to sort of fill them with these cryogenic liquids at least every second day. And when you have done all that, you were never sure that they actually worked anyway. So that was sort of, so it was a very scientific experimental sort of environment. So it was very hard to commercialize or make it more industrial, and you use it for applications. So this is what the founders of Blueforce changed. They made use of new technology to sort of mitigate the problems that actually existed. And a system today, this is a standard Blueforce system, looks like this instead. It has an easy user interface, and it has a rather clean and clean sort of experimental space that you don't need to entertain by filling liquid cryogenics and etc. And this, of course, also have enabled applications. As I said, cryogenics doesn't really need to be visible anymore. It doesn't have to be steam and smoke. It's sort of, this is how it looks. It's just a computer interface in principle that you are utilizing. This picture is actually from D-Wave that does quantum annealing, which is sort of a sort of beginning of quantum computing. And these, of course, they give the impression that cryogenics is not a problem. So what did Rob and Peter do 11 years ago? So they made use of mechanical coolers. So they could replace the pre-cooling that was done by cryogenic liquids with something called a pulse tube. So it's a mechanical, so you only need power and cooling water. So it was natural infrastructure that you have in industry. So usually that's called a cryogen-free or a dry system. But that was not everything that was done. As I said, you were never certain that it actually did cool down, even if you did all the things correctly. So they also redesigned the whole system, made it more robust and reliable. And I think that is more a key point why the cryogenics, especially the dilution refrigerators from Blueforce, has been such a success in this field. This redesign also made it possible to make a larger and more accessible experimental place. So you actually had room to develop this technology, the quantum technology, for example. And the usage, everything can be automated. You can push the button and you can actually go away for 1 year and it's still cold when you come back in principle. So this, of course, these advantages, of course, have enabled cryogenics as a tool and for the community. If I look from Blueforce point of view, the way it was constructed, it also enabled scalable production. And since you have enabled a scalable production, you can also grow with the demand. So that's the reason Blueforce have been able to grow at the speed that they have, because the demand comes from agile companies like software companies, where they have a completely different understanding of how fast progress should be. And this is an industrial production, but these changes have made it possible. So I would like to, in the old days, cryogenics was always a problem. So there was cryophobia from industry, you don't want to invest in that. But now cryogenics is actually a possibility. It actually enables new technology instead of creating a problem. To give you an overview of what our products are, so this is the dry dilution refrigerators. So they are, this is sort of the basic system, and it consists of 3 parts. You have an experimental space, which is in principle a vacuum chamber where you put your experiment. And in that one, you have a cooler that is run by a gas handling system. It's actually behind here, it's quite compact. And that's the heart of the system that drive the coolant around to get the system cool. And then there's a control electronics for controlling and automate the operation of the system. In this place here. So inside this vacuum can, you have one of these. So this is the dilution refrigerator inside. So this one consists actually of many coolers. And I mentioned this mechanical cooler, so it's this pulse tube that sits here. That one does the trick that liquid cryogenics did before.
But the computer is on the top of that plate, on that shiny part.
It's below and on top. You can put it where you want. It depends. There's more space underneath. So you only need to have the thermal contact to the interface. But a computer is more than just the chip itself. You need the whole line of this system. I will tell a little bit more later about that. So this top part here is cooled down by this mechanical cooler. And then the lower part, that's the dilution refrigerator unit. So what you see here, the shiny thing here, that's the thing that takes the system down to very low temperature. So it's below 10 millikelvin. This is sort of our product lineup. So the first system we made was this size, and then the evolution of the company has just made the systems bigger. And the reason is that the experimental infrastructure is getting bigger. They need more control and more readout of the system, and especially in quantum computing. So where are our products used? So of course, they are used in quantum computing. We got a good introduction by Mikko already. There's also detectors especially for basic research. They use detectors to have much higher sensitivity, so they need to cool them down. Material science and nanoscience, you study phenomena as a function of temperature. And of course, basic research, you also use these detectors to actually monitor something that is sort of natural phenomena. So this is actually a cryostat mounted on a telescope down in Chile. And it has a detector array on the end of the fridge here. And it's going to measure the background radiation of Big Bang and sort of get a better map of that in the future. So, as I said, Mikko never mentioned cryogenics, but why is it needed? So most of these quantum systems, of course, they have a finite, like this 0 and 1 that Mikko was telling about. Of course, you can drive that system when you have interference. And so what you want to do is you want to minimize any external noise or environmental effect on these systems. So we are working in this field. So we are lowering the temperature to make it possible. So some of the quantum systems, they need millikelvin temperature to operate correctly. There's of course other things. Dissipation from electrical readout circuitry of your devices might interfere with noise, and also their temperature is important. So you might need superconducting conductors to reduce resistive dissipation of your system. So there also temperature plays a role. And then electrical EMI environment, for example, is also important to not disturb the quantum system. And here, low temperature maybe is not so critical, but if you need magnetic shielding, superconducting shields are also good. So there is always a need for cryogenics in this context. So Mikko already told a lot about quantum computing. I just listed a few sort of quantum computing qubit systems that actually need cryogenics to some extent. Superconducting qubits was already described. Semiconducting spin qubits, very similar when it comes to the infrastructure you need from a cryostat or from cryogenics. There is the promise of a topological protected qubits, and I think that also will require low temperatures or cryogenics in the future. Photonic qubits is something that inherently the photon or the qubit itself don't need low temperature, because usually this is optical qubits, so they can operate at room temperature without problem. But they need to sort of read these qubits out. They need single photon detection, and then you need to go down to cryogenics again. So this is sort of it always comes back. So cryogenic there is something fundamental why we need to cool down either our sensor or our systems. And it has to be, how do we actually control nature? We need to sort of do something to the environment first. I don't know if it's universal, but that you guys can answer me later maybe. So where is Blueforce in all of this? So of course, where we are now, we are doing generic coolers, and it's for R&D. And the customer, sometimes they do the whole measurement infrastructure themselves, or they buy parts from us. So that's where we sort of have seen that there is an added value for Blueforce to add customized solutions, add special functions, improve the measurement infrastructure already when they buy the system. And of course, we also like to develop and commercialize cryogenic components that only exist in the lab, and now there's sort of a ramp up needed for many of the quantum community, because they need a lot of these tools. It's not only one in the lab, it's maybe hundreds of them. So that's where we also see our role to add value to customer. So at the same time as quantum technology actually is enabling cryogenics, it's also working the other way around. Since we are working cryogenics, we can also make the solution that boosts the quantum technology. So again, I want to stress, it's not a problem, it's a possibility. And something that has been noticed the last few years is that traditional suppliers of components in microwave and electronics, they never want to go to cryogenics. But now they are coming and want to do something for cryogenics. So that is sort of a change in attitude. And that's something to harvest also. Because it's not only for, well, quantum technology in itself, but cryogenic community will benefit a lot from this because you can actually take it to the next level. So if I look at the next step that Blueforce see from our point of view is threefold, if I do it simply. So one thing is what we already are doing, but we can go further to improve the measurement infrastructure. Another opening field is, of course, there's other tools, not only the R&D experiment. Of course, when the fabrication of all these quantum chips is sort of ramping up, you need tools to actually characterize and do statistics on the processes. So this is where we also see a niche for cryogenics, and that's where Blueforce try to sort of make an impact and sort of make tools that will aid this. And then, of course, at one point, the coolers will just be part of the application. So there is, of course, going to be customized systems that are specific for that application that they're going to be needed for. So it's not going to be a generic cooler anymore. It's going to be a specific cooler for that application. So if you take the first one, improved measurement infrastructure. So why would you need it? Because, of course, you get the low temperature, but what do you need more? So, of course, you need higher density of integration because in detectors, you want to have more detectors, which means that you need more control lines and more readout lines. In photonics, if you have the single photon detector, for example, if you need to read out more and more, you're going to need more inputs and more sensors to sort of be read out. So you need an infrastructure that allows you to have more and more measurement infrastructure in your system. Cryogenic electronics is a very hot topic. There's both CMOS version, which is more semiconducting based, cryo-CMOS. Superconducting logic has been around for a very long time, but they are never been good enough because they are still classical. So it's a little bit the same as with analog computing. But that also, the more complex this logic becomes, the more inputs and outputs you need. And of course, quantum computers. When you start to having 100 plus qubits, you need a quite enormous infrastructure in the cryogenic environment. So high density integration is of course important, but at the same time, when you do that, you also have to make it easy to maintain. So you cannot just do like we do today. So this is one of our systems where we have maximum amount of coaxial microwave wiring. So there's 330 lines here. But if one of these breaks in the middle here, it's not fun. So this is of course something, it's okay on an R&D scale, but of course in a more commercial application, this is not okay. You need to have something that can be maintained much easier. And of course the system itself much allow for redundancy. You should be able to sort of quickly replace if something goes wrong. Coming to the tools, so we already been active there. So we have had a very successful collaboration with Afore, a company here in Finland too, Lieto, outside Turku. Aki is here today, he's one of our collaborations. So what we did here, we combined our cryogenics with Afore's cryo probing or wafer probing technology to build a system that didn't really exist. So as I said, you're going to need to start qualify your processes, do statistics and do characterization at a much higher rate than putting them into a cryogenic system and wait for a very long time and then do another one. So this will be a system that actually measure the samples at a low temperature, and you get the sort of characterization that should aid you in getting a good process for fabricating these devices. There's a lot to tell, but it's based on the same pre-cooling with the cryogen-free environment, so there's no cryogenic liquids needed anymore. And it's actually made to be compatible up to 300 millimeter wafer. So it's actually ready to sort of be adapted in sort of the most of foundries around that will do cryogenic fabrication. If you want to know more about that, I can tell you later. So what are the next steps for Blueforce? Of course, investments in this field is needed now because there is a big momentum. So Blueforce is really trying to sort of keep up with the demand and trying to serve it so it actually keeps on growing. So of course, investment is a big part, and of course, collaboration. So what we do internally is that we, beginning of last year, we actually bought the whole facility that we were in. So we now have 9,000 square meter of production space. And there is a huge renovation going on, and this should be ready, I think, end of next year. We have done the complete renovation of the facility. We invest a lot in in-house production because we have noticed that it's much easier for us to sort of answer the demand by have the capabilities in-house. So this is something that is going on also. We have a quite very well sort of equipped workshop that sort of produce most of the parts in our products. We also need to be able to assemble this system, and to ramp that up, we now have a new cryo hall. It's actually getting ready next month. It's actually very close to finalization. And this have capacity to actually produce 40 systems at a time. So that is to sort of, it's over capacity, but it's a way to sort of not make our production the bottleneck in this game. So. And of course, the collaborations, I just mentioned Afore. This is probably going to be more collaboration with other entities to sort of drive the technology forward. We also look at the scientific community. We have Open SuperQ, which is part of the flagship. And we have this European microelement platform, which is looking more into the aspects of cryogenics. And then something that is sort of in the making is sort of trying to build a co-innovation building. So this is something VTT is coordinating, where quantum technologies are sort of combined and sort of finding a strategy for how to make even more sort of development in this field. So I think that was, am I still on time? I have a little bit over. But that was what I had to say. Thank you.